All right, so mainly I've been focusing on the wrist rockets, improving that performance, but I really want to take a shift on focusing on the wearability of the suit. That's a whole project in and of itself for the entire suit, but the forearm and the bicep and the entire arm itself require some level of consideration for how it's going to attach to me. All the flashy, systems that we have to do, like the flamethrower and the rockets, those are all pretty cool and very important to how I want the suit to function, but the actual wearability of the suit, the donning process, how I'm going to wear it, how it's going to attach to me, how it's going to lock in place, all those features are even more important for the actual final functionality of the suit. If I can't wear the suit, it can shoot rockets, it can shoot fire, it can do all that, but if it's not wearable, it kind of defeats the whole purpose of it being an Iron Man suit. And what I mean by wearability is really just like Iron Man 1, the Mark III suit, right? That famous scene where the suit kind of gets assembled around Iron Man. That whole process is really the core foundation of this project. Not really replicating it one-to-one in the movie, but being inspired by that to kind of implement some of those ideas. There is a necessity for the suit to be able to be easily taken on and off, otherwise it becomes like a costume that I have to slip on, like something I bought at Party City. I want it to be more technologically driven so that the actual suit assembly process is a lot more intentional than it is kind of a second thought. So looking at that scene, what's happening is the suit is getting assembled with these robotic arms, but what happens is that once they're in place, the kind of internal mechanisms that are designed into Iron Man's suit take over that final assembly process and finish locking everything in place. I'm thinking right now, for complexity's sake and also to save a shit ton of money, that I'm going to focus more on the intermediate stage where the parts are technically already in place and the internal mechanisms of the suit take over that assembly process. So maybe we're leaving the door open for robotic arms in the future, because that would obviously be super fucking sick. But for now, we're going to start off as the suit partially assembled, kind of opened up so that I can fit my arms and my other body parts through, and then it'll close around me so that it kind of secures and locks in place and becomes more like an actual exoskeleton. And what this allows us to do is compromise a bit where we can have some wearability aspects built into the suit, but not to the point where it's like in a bunch of different pieces and panels, like in Iron Man 3, where his suit is a bunch of different pieces that kind of fly together, to make the entire suit. That is an insane project, because in order to do something like that, even without the flying components, you have to imagine that all the stuff that makes up the subsystems, like the rockets, the flamethrowers, the blades, everything in that system would have to be split across all these different pieces and then somehow come together and then still work the same that we would want them to, and that's kind of ridiculous. So this intermediate step where the suit is kind of mechanically opening itself up for me to fit through, I think that's a good starting point in terms of implementing some sort of wearability process, and it'll leave the door open to kind of do more complex, cool stuff in the future. So looking at how we want to do this, we can also look back at the Mark I suit, as there was some design in there as well, and you can see what I did is I had these latches on the forearm and bicep that you would unlock and then basically open the forearm and put your arm through, and then you would close the latches, lock them in place. And that added a level of kind of intentional wearability where the suit had a process of putting it on and off, and the bicep itself also had these latches that opened up and put the arm in and everything. So that's kind of my initial starting point in wearability design. Clearly the system is very simple in terms of the wearability process, but it allowed me to do a lot of the test. So it wasn't necessarily useless. But in terms of kind of matching the technical sophistication of all the other subsystems on the Mark II, we need to take this to the next level. And my first idea was, what's a way that we can very easily actuate on a similar system like the Mark I? The Mark I uses 3D printed hinges that are super weak. Maybe we make them out of metal. Maybe we make one of the hinges a motor that kind of rotates the forearm and bicep so that they open up like the Mark I does. But in that design process, you kind of start running into the problem where the forces required to open up the forearm, which is loaded with all these subsystems, end up being quite significant because it's on a pin joint, and the point that you're actuating at has a huge lever arm that creates this giant torque that you'd have to oppose and kind of deal with. So it would end up being a huge motor at the hinge that would then draw a lot of energy and kind of cause all these problems and be bulky and stick out. So I decided to kind of switch from hinging at the side of the forearm to maybe hinging at the base, where the bottom forearm kind of drops out from the top forearm, and it's more of like a jaw motion where it's like opening up wide enough where I can stick my arm through and then it'll close up. And I had these cables that were kind of routing through the top forearm, holding the bottom forearm, that allowed it to kind of wench up and down with some motors in the back. I think from a mechanical design standpoint, that kind of makes a lot of sense. I think it's a pretty straightforward mechanism that probably would have gotten us where we wanted, but I was a little concerned on the robustness because maybe the cables would be too weak, there might be some slack in them. Unless we keep the cable always in tension by kind of having the motors apply a little bit of like a constant force, which could burn a lot of power, and I wasn't looking forward to doing that so much. And I was also not necessarily super happy with the look of the design. It didn't really match the Iron Man-like feel that I was going for, so I kind of switched away from it. and actually kind of wanted to get more inspired by the actual Iron Man suit design and how that one assembles itself. So then for my suit, I kind of took a lot of inspiration on the linkage design and added a bunch of little linkages across the top and bottom forearm. What I was thinking is that I could have the top and bottom linkages be actuated so that they would kind of collapse together and it would force the bottom forearm to align with the top forearm. And then the reverse of that motion would basically drop the bottom forearm out and allow me to put my arm through. It ended up being this kind of complex linkage system where I had these cross beams that would kind of mechanically couple each row of linkages together so that I wasn't individually actuating each linkage. But since I had the bottom forearm kind of following this weird path, it ended up resulting in linkages of different lengths, and those cross beams would have to change position on some of the linkages to account for the fact that the linkages were rotating at different angles and doing a bunch of different things. So I had to add these extra sliding joints for the cross beams to move along so that they could accommodate for the position of the linkages, and it ended up kind of working to an extent. There's also a lot of issues with the actual accuracy of the parts that I had. In order to have those little linkage sliders, there was a lot of small details that needed to come out right in order for it to work as I intended. And basically because kind of tolerance stacking and air propagation, and then ended up being that the system had a lot more friction than I intended and kind of made the opening and closing process not as smooth as I wanted. And there was a lot of added complexity with all these different linkages and bearings and pins and everything. By the end, it was kind of like a mechanical mess that kind of started looking promising in terms of the visual aspects and the potential mechanical aspects. I mean, we know the actual mechanical functionality would work since we see it work in CAD, but in real life, it kind of ended up being this semi-functional project. But I wanted to see if I can make it more easy to work with and not as complex and crazy in this whole thing that involves all these different components that are weak points. And the reason the forearm was following that specific path on this design was that basically I wanted the front to be open a lot more than the back, since the back is a lot wider and my hand can fit through a lot more easily. So that's kind of where this interesting shape and kind of movement pattern came from, which led to all the linkages being all these different sizes and ended up resulting in a bunch of mechanical compensations for that motion. So that was the main source of the issues for that design. But I was thinking if I really just focus on the tip of the forearm, it's also totally fine for me to have a design where the actual front of the bottom forearm is equally as far out as the back of the bottom forearm, and it would basically just give me even more room for my arm to stick through. So because of that, I decided to take a more symmetrical approach to the linkage design, making them all the same length so that any sort of cross beam between them can mount at the same point and doesn't have to slide between different points as they rotate out. And also they would all rotate at the same angle so that the positions also stay consistent. And basically that creates kind of a pseudo 4-bar mechanism. At the core, that's really what it is, pretty simple. But since we're meeting two 4-bar mechanisms in the middle, it kind of gives it a little bit more of an extra level of mechanical design, right? But the trick now is to actuate those linkages so that they do the closing for me and not me having to just lock them in place with magnets or something. And that's kind of landed me more on this design. So I wanted to get a more low profile, sleek design that really fits more in the spirit of the actual suit itself, which really made me want to use linear actuators, but a lot of the ones out there are too big and kind of clunky, or they have, the shaft, which is really thin, but then they have a motor off to the side that's also adding a ton of space. And then I eventually came across these things called pen actuators, which are really cool. It's basically just a super compact linear actuator and provide just enough force to actually open the mechanism to the point that I want them to be. So I ended up using that on this new design and kind of going forward with that. As the design progresses, it really seems to be satisfying a lot of the requirements I had for this project. It's very compact. The pen actuators actually accomplish the motion that we want, moving the linkages up and down. I tested the basic motion on a 3D printed prototype, so not necessarily the most accurate one-to-one of the final design, but it gives us a good insight into how well the mechanics line up. And with the cross beams, they can actually be a very weak point since they're so thin and small, just to keep a low profile. But if we take advantage of 3D printing out of metal, we can make these very robust cross beams out of titanium. That should work pretty well and accomplish the goals that we want. And now moving forward, it's a matter of really seeing how the two top and bottom forearm mechanisms mesh together. Ideally, once they're connected through the pin joints, they should be able to open and close very easily. I think of all the actuator solutions I've tried for the donning process, these seem to be my favorite in terms of profile, power, and speed. So I'm really interested in seeing how they perform at the end of all this. What we need to do now is start looking more into the actual full control architecture of the donning system. The mechanics seem to be working pretty decently, but we have to make sure that we have motor control where we can track the endpoints of the closing and opening sequence. And to solve that, my first design is basically using magnetic limit switches. So taking a very similar approach to the side blade design that uses a Hall effect sensor to read magnets over two different positions. One of the linkages now is dedicated to sensing, where the linkage itself extends a little past the actual pivot point, and a magnet mounts on that point and swipes between two Hall effect sensors that will give us the start and end points, which we can then use to extrapolate the distance and speed that the other motors need to move in order to make sure that everything ends at the exact same time. Basically because the top forearm actuators and the bottom forearm actuators have to displace slightly different distances, because we know both actuators need to make the linkage arrive at its endpoint at the very same time, but since they're displacing slightly different amounts, that means it's going to have a slight speed difference, which you can use the Hall effect sensor and then the motor speed controller to then have all the actuators end at the right point at the right time. So the control logic doesn't seem too crazy. We don't need a full closed loop control with an encoder and all that yet. I think maybe at some point that might help with the accuracy of the motion, but for now, keeping it as simple as possible to just make sure that we have a working mechanism, I think is the right way to go. And then also on the actual motor driver side, previously for a lot of the other motors that require a little bit more power, we use these higher power, larger motor drivers that kind of handle higher currents and higher voltages. Luckily, since these pen actuators operate at 5 volts and have around 200 milliamps of current draw, we can get away with these tiny motor drivers where we can have 2 motors being controlled by this tiny driver, which we can then feed into our ESP32 architecture and save a lot of space on the bottom of the form, which we're starting to populate with more and more PCBs as we increase the overall electrical ecosystem of the suit. But everything seems to be going pretty well so far. It's going to be exciting to test how the actual arm itself attaches to me. But that's really just the start of a much larger project that takes over the entire suit. Now that we have donning on the form, we have to do it on the bicep, eventually the glove, the chest piece, the legs, the mask, all that stuff that Iron Man would do. We have to eventually implement that. But luckily, I think the form is a really good platform for us to learn on what mechanisms work best in order for opening and closing stuff and controlling different panels on the suit for wearability, but also looking out for the rockets because that's coming along. I've been putting together the custom motor to get it assembled, also working on a side bring up of both the rocket barrels so that we can do a dual test of the old system with the gear train, just to get more familiar with the system as well. There's a lot of stuff that we still don't really know. Only done one super successful experiment, so we need multiple tests to get more data. So that'll be fun. And then after that, we're gonna keep going on everything else. It's a full suit that needs to be built eventually, but we're making progress for sure, so stick around.